Okay, lecture 15, Epilogue. So the real lecture has ended the last time. So this is just the epilogue. And what I would like to do with this one here is to see what we have done in this course and find out or tell you where we are going after this. Okay. All right. What we have learned in this class? Well, we have learned that a robot consists of links and joints. So therefore, a robot is nothing but a multi-link mechanism. You have a bunch of links and connected by joints. Okay. So the posture of a robot is a set of joint angles. If you decide the joint angles for every joint, you have one posture, one form of a robot. So a vector of joint angles is the posture. Okay. And motion, robot has to move. When the motion moves, variation of joint angles vary, changes the joint angle value. So that means time varying vector. Yeah, all those angles will have speed, non-zero speed. So convenient tools are calculus and linear algebra. And calculus is for the time varying vector here, the motions, and linear algebra for the vectors for representing the relationship and the form or the posture of the robot. And in calculus, we learn chain rule, which are very useful actually, and Newton's law, which is in the form of Newton's law. This pretty much is a basic for every motion. This is, say, tau is equal to I theta double dot. That is the equation for the rotational motion. Table of derivatives, yes. Well, derivative is defined by the limiting operation of the differences, right? But you don't need to compute the limit of the quantity. Instead, you have a table of derivatives because we are engineers. And applications are Jacobian matrix. Wow, this one was very, very, very. Okay, this Jacobian matrix very important, right? Because Jacobian matrix will give you the relationship which can be used to find the end effector speed in terms of the joint speed or fine adjustments. And Jacobian will tell you whether it is possible or not. And also, data processing, you set the partial derivatives equal to 0. That's the start of the normal equation. So calculus is very useful for that. But anyway, those are useful, but since we are engineers, we should approach our problems from engineering point of view. That's why I gave you so-called axioms. Like speed is differentiation. We all know now. And divide and conquer. You divide big problem into small problem. More fish under willow tree, yes. If you can use a tool once, then you should expect that that tool will be useful one more time or two more times. Do nothing. That's mathematician's tool. Okay? So where do we go from here? We learn more robotics related tools. Okay, we have learned the two major tools, linear algebra and calculus. Okay? But there are kinematics, dynamics, discrete mathematics for computers. Because in controlling your robots, you have to use the computers or a microprocessor, whatever. But as I said, last time, or not last time, but the time within the computer does not move continuously, right? There is a concept of clock pulse. So the time runs discretely in a computer. So that gives us a whole new world, actually. So we should have discrete mathematics for computers, which is quite different from what we are used to. Like differentiation, you're gonna do it. Like integration, you're gonna do it. So using those, you're gonna come up with so-called control techniques. And control techniques probably someone's PID controller. Those words, it's just a word for you right now, but you will hear those words quite often. Programming, of course, including I/O, and image processing, AI, etc., etc. All of those are theoretical part, but of course you will learn hardwares as well, like electrical and electronics circuits. You know the difference? Electrical meaning that the large current, like moving the motor. Electronics meaning that signal. So current is not very large, but electronics, it carries the signal. Microprocessors, ADDA converters, motors, structures, and sensors, etc. Structures meaning that you will learn how to design robot structure. So you will learn all of those, and what is a keyword? This is the word I would like to give you. Integration. The robotics is different from many other disciplines like electronics or mechanics or computers, etc. The major difference is this integration. We need to integrate lots of different things into a thing called a robot so that it will work as we want it. Okay? And I hope that you will learn those tools and you use those tools to come up with your nice robot. Well, thank you very much for listening to my lecture. This is the real end of my lecture. Thank you. Bye-bye.